Welcome to The Explainer. Today we're unpacking the invisible rule that governs absolutely everything around us. Seriously, whether you're dealing with extreme high-speed machinery or just going about your normal morning routine, there is a fundamental law of physics quietly running the show in the background. So, let's dive right in. I mean, what on earth could possibly connect launching a massive 2,100-kilogram rocket sled across the desert at breakneck speeds to a kid simply kicking a soccer ball in the park? They seem like entirely different worlds, right? Well, it turns out we're going to discover exactly how these vastly different events are dictated by the exact same universal law of motion.
All right, Section 1, the ultimate rule of motion.
Let's get right to the core concept here. The formal definition of Newton's second law of motion states that the acceleration of a system is directly proportional to the net external force acting on it and inversely proportional to its mass. Okay, I know that's a bit of a mouthful. But in short, this law tells us something highly intuitive. A net external force acting on a system from the outside causes that system to accelerate. Basically, if you push something, its speed or direction changes. It's that simple.
And that brings us to what is arguably the absolute fundamental equation of classical mechanics. You've likely seen this written on a whiteboard at some point as F equals ma. That just means net force equals mass multiplied by acceleration. It's a wonderfully elegant formula, honestly, because it neatly ties together three completely independent physical quantities into one universal rule.
Now think about the second half of that definition, how acceleration is inversely proportional to mass. If you apply the exact same physical force to a lightweight basketball, it causes massive acceleration. That ball is going to fly across the court. But if you walk up to a heavy, stalled SUV and apply that exact same push, yeah, it barely moves. The larger the mass, meaning the more inertia the object has, the smaller the acceleration produced by a given force.
Moving on to Section 2, decoding force and mass.
Now that we've got the basics down, let's see how engineers actually use this out in the wild. The history here is incredible. Prior to human space flights in the early 1960s, scientists used these massive rocket sleds, propelled by 4 roaring engines, to test human endurance at extreme speeds. By understanding Newton's second law, they could safely calculate accelerations reaching a mind-bending 45 Gs.
Let's actually crunch the numbers real quick. By carefully defining our system, which is the sled, the rockets, and the rider all combined, we can logically walk through the math. We've got a total mass of 2,100 kilograms and an acceleration of 50 meters per second squared. We also factor in a friction force of 650 newtons dragging it back. Using our F equals ma equation, we find that the total thrust required is astronomical. Divide that by the 4 engines, and each individual rocket has to exert a massive 26,000 newtons of force just to achieve that acceleration. Absolutely wild.
But here's the beauty of physics. You don't need experimental rocket sleds to see this law at play. The crucial point is that this exact same mathematical framework applies when you simply step outside and push a 24-kilogram lawnmower across your front yard. Let's say you apply a net forward force of 51 newtons, which is your pushing force minus the friction of the grass. But dividing those 51 newtons by the mower's 24-kilogram mass, we find an acceleration of 2.1 meters per second squared. So as you can see, the exact same rules that hurl humans towards the stars also dictate a perfectly normal walking speed for a person doing Sunday yard work.
Okay, Section 3, the mass versus weight mix-up. We throw these terms around interchangeably in everyday language all the time, but confusing mass with weight is actually a major scientific misstep. So what is the actual difference? Well, mass is the actual amount of matter, the physical stuff inside an object. It's measured in kilograms, and it never, ever changes in classical physics, no matter where you take it. Weight, on the other hand, totally different. Weight is simply the downward force of gravity acting upon that mass. Because weight is a force, it's properly measured in newtons, not kilograms.
And here is the equation that proves it. Weight equals mass times gravity, or W equals mg. Notice how similar that looks to F equals ma? That's because weight is literally just a specific type of force. And because weight depends on the acceleration due to gravity, your weight actually changes depending on where you happen to be in the universe. To put that into perspective, let's take a standard 1-kilogram mass. On Earth, gravity accelerates objects at 9.8 meters per second squared, meaning that 1 kilogram mass weighs 9.8 newtons. But if we transport that exact same object to the moon, where gravity is vastly weaker, its mass remains exactly 1 kilogram. It still has the same amount of physical matter, but its weight drops to a mere 1.7 newtons. So, fun fact. Think about this the next time someone talks about a new diet. When people say they're losing weight, scientifically speaking, they're using the wrong terminology. They actually mean they are losing mass. They're actively trying to reduce the amount of matter in their bodies, which in turn naturally causes the gravitational force acting on them to decrease.
Which brings us to Section 4, Physics in Everyday Life.
Now that we've decoded the math and cleared up those weight and mass misconceptions, let's explore how you're using Newton's second law constantly, probably without even realizing it. The everyday applications are literally endless. Racing car engineers obsessively strip weight, well, mass, out of their vehicles. Lowering the mass ensures the engine's force results in a much higher acceleration. Similarly, the devastating impact force of a car crash is entirely dictated by this law. A heavier vehicle moving at high acceleration produces a terrifyingly high impact force.
Consider the physics of a karate chop. It looks like movie magic, but it's just Newton's second law. When a karate player breaks a solid slab of bricks, they aren't just relying on huge muscle mass. They're moving their hands incredibly swiftly to gain immense acceleration. Because force equals mass times acceleration, a massive acceleration of the hand produces a proportionate force that's strong enough to instantly shatter solid material. It even dictates something as simple as walking. If two people are having a walking race, the person with less mass requires far less internal muscular force to accelerate themselves forward. Mechanically speaking, it's simply easier for a lighter mass to generate forward acceleration compared to a heavier mass applying the exact same force.
So here's the crucial takeaway. You are essentially a walking, talking physics experiment. The next time you kick a soccer ball, push a heavy shopping cart down the grocery aisle, or feel yourself pressed back into your seat as your car accelerates onto the highway, remember, you are a living, breathing application of classical mechanics. And that brings us to the end of our explainer. But I want to leave you with this final, slightly philosophical thought based entirely on physics. If your mass remains constant everywhere in the universe, how will you use your unique force to change the acceleration of the world around you today? Thanks for exploring Newton's second law with me, and keep questioning the mechanics of everything you see.